Okay, thank you very much for having me here. I hope you will understand my English pronunciation, and I also hope that that machine will understand me, because sometimes it shows funny things in English translation. So I hope it will work well. I came from Europe, from Germany, and I will talk about quite low-level things. There have been many amazing talks about AI, and I hope next year, if I would be here, I would also be able to contribute. But in Europe, situation is that clients are usually afraid of AI still, and they battle with quite basic stuff when it comes to Postgres and Linux, because the typical situation is they start with a very small setting and they want to put more and more on that machine, and they sometimes don't understand why too many connections on Postgres could be really hurting performance. So I have actually several talks about these things, and this is one of them. It explains why too many connections are simply too many. So I work for a German company called Credative. In Western scope, we've been one of the first companies offering support for open source products, but now we also offer some complex solutions with Kubernetes and Proxmox, and complex migrations from old or proprietary databases to Postgres. Few words about me. I am quite an old guy, and I grew up with dawn of personal computers, and the whole my life was about data processing in different ways. So I worked with many different databases, different data ingestion pipelines, and lately I do the same stuff also with AI. I will really thank to PostgreSQL community for supporting my participation on this conference, and also many thanks to Hygo company for the opportunity to test on Fitium server with NUMO architecture. On Sunday I had here 3 hours workshop about shared buffers where I talked more about this testing. Here I will only touch it very small way. Here are a few words, a few notes of what I will show you. I will talk mainly about Postgres 18 and Linux kernel 6 and Intel AMD x86 architecture, which is a typical configuration which we see by our clients. So, as we all know, Postgres uses multiprocess architecture, and this architecture, of course, has its limits when it comes to number of connections, and typically on configurations which our clients have 300 to 400 connections on Postgres is limit. After that, performance starts to degrade very badly. But they sometimes don't understand why it is happening. So we need to explain this stuff. Here is just some summary why this architecture was chosen. It was actually the best architecture in 1990s when Postgres was designed, because reliable threads have been implemented into Linux much later. And of course, independent processes have many advantages, like they have isolated memory areas, higher security, but that overhead with switching between processes can be quite big. And Bruce Momjin talked actually last week in German conference about what we will have in future in Postgres, and he mentioned that most likely in coming years we will have mixed architecture, similar way how Oracle implements it, so we will be able to choose between processes and threads. Those independent processes on Linux must communicate in some way, and this communication is done using shared memory. And because in Linux philosophy everything is a file, this implementation is done also as file system. It is specialty MPFS file system which has two components, which one of them is visible to clients, and second is internal mounting point. And that internal mounting point is used for shared buffers. And in slides from my workshop from Sunday, you can find more details about it. They should be already publicly available, so don't hesitate to look at it. This is that part which clients usually see. This is that def shm special directory, which behaves like a disk, but it exists in memory, and it's actually direct interface into memory, and it allows us to read and write into those files, and that way actually change context directly in memory. There is just small note that on Docker and similar systems there could be some small limit, and in that case we need to increase it, but I think we already encountered it here. So when it comes to Postgres connection, the biggest issue which can raise is by how memory is allocated if clients actually stick to standard 40 kilobyte pages. Linux implements a quite ingenious system of tables to store this memory mapping, and it is done in this hierarchical way, because if we would want to translate 64-bit virtual addresses to physical addresses using one table, it would be a really performance bottleneck. So there could be 4 or 5 those tables, and those standard 4 kilobyte pages, they lived in that lowest level in a page table entry. Fortunately, we have these huge pages, and 2 megabytes huge pages are on the level above it, and 1 gigabyte huge pages are in this middle level. And it has, of course, its consequences for also consumption of memory necessary for these tables. As we all know, connections are created by forking main postmaster process. And this forking is fortunately done in very light way. So even if postmaster already maps whole capacity of shared buffers into physical pages, only very small part is being copied into that connection. But of course, when connection starts to touch those shared buffers, it needs to get those memory allocation into its own tables. And here comes that issue with the way how those shared buffers are being configured. Because if we use those standard 4 kilobyte pages, then 1 gigabyte of shared buffers in these 4 kilobyte pages requires around 2 megabytes of PTE tables, which of course means that if you would have too many connections, and here is some simple calculation for 1000 connection with 8 gigabyte shared buffers, then if those connections will step by step map the whole capacity of shared buffers, those PTE tables can theoretically reach 16 gigabytes. There is actually a link to article from Percona which checks these things. So when slides will be available online, I highly encourage to look at that article, because this problem can be actually quite huge. Fortunately, when we recycle connections, these things are not that problematic, but I have seen clients who keep connections living like 4 days, weeks, and in that case, those PTE tables, if we have shared buffers in standard pages, they can grow really, really big. On the other hand, if we use 2 megabytes huge pages, then situation is much nicer, because for 1 gigabyte of shared buffers, we would need only 4 kilobyte that middle directory table, which means for 1000 connections and 8 gigabytes buffers, so just something like 32 megabytes of those middle directory pages. This is one reason why configuring shared buffers in huge pages is a really good idea. In those slides from that workshop, there is actually explanation how precisely configured shared buffers in huge pages. We now have also huge machines with NUMA architecture, and now rises the question if that NUMA architecture adds some additional penalty. I had opportunity to test on that Fitium machine, and that Fitium machine had 8 NUMA nodes, only 4 of them had memory, and there was some theoretical table of penalties, of distances between those nodes. This table is actually hard-coded in firmware, and it's part of that machine, but those numbers are just theoretical because they are just increased by 10 between those nodes. So theoretically, the worst situation in this type of architecture was if node 4 would access memory on node 6. And I did some testing because we can also on NUMA architecture pin Postgres to specific node or group of nodes. And in that case, of course, if we pin postmaster, it means that all connections will inherit this pinning and will follow it. And as far as I can tell from tests I could do, I did not see any big differences in use cases I was able to test. I tested some mainstream use cases which are typical for our clients, and benchmarks were actually looking quite good, and differences between results have been like 2 to 6%, which is not statistically significant. So from my perspective, what I could test on that machine, those mainstream use cases, that pinning actually was useful only for isolating Postgres on specific nodes. But if I used the whole machine with that interleaf value for pinning, then Postgres used all those nodes and all available memory on those nodes, and I did not see any penalty. But again, it was just this type of testing. Definitely there could be some cutting edge cases when actually this will be significant. But from perspective of my test, I did not find anything which would suggest that that NUMA architecture was hurting performance in some way. We have more pressing problems, which when it comes to many connections which are on database, and one of them is problem with context switching. I think we all know how it works. Process run on CPU, it is interrupt, its state is being saved, and then state of another process is being loaded to CPU, it is processed for some time, and again work is interrupted, state saved, and the whole game is repeating again and again. And here we have some consequences if we would have huge shared buffers mapped in those small standard pages, because there is something called translation look-aside buffer, which actually translates virtual pages, virtual addresses into physical pages. And we can have many misses, and of course repeated need for flushing this buffer. And another thing which is coming with a new version of kernel is change of a scheduler. Older version of Postgres had so-called completely third scheduler. And idea was quite nice, like I have several processes, so I give those processes fairly the same portion of time, and it should work for everyone. Yeah, well, in those days when it was designed, it was true, but in these days we have a lot of online processing, and completely different requirements for latency. So, for example, in this first graph, that completely fair scheduler, if I have audio stream, which is that greenish part on the top, latency matters. And therefore, Linux now implements new scheduler, which is called earliest eligible virtual deadline first. It's a very nice name. I had to train it to be able to say it. And it means that that scheduler tries to guess which process is sensitive for latency. And this sensitive process gets runtime more times. Of course, in longer run, that runtime of those processes will be exactly the same, but that sensitive process, which needs low latency, will be running more times in that CPU in smaller parts. So if I have this audio stream here, you can see immediately difference in latencies in processing of that process. On the other hand, this reddish example, this is some compiler. This compiler will definitely love to run longer in longer intervals on that CPU. And this change is coming with Linux kernel 6, which means that clients are already seeing differences. And that difference is that if we have transactional workload on Postgres, or if we have some content management system which actually fires many very small queries, this is typical situation with this software, because it needs to read a lot of small data from database, meaning some permissions to objects or position of objects and so on. So if we have this type of bursty workload, it means that this type of workload will see improvement, because these short queries are actually sensitive to latency, so they will be processed quicker and more often. On the other hand, there are some fears about classical analytical workload, because if we would have machine with only analytical workload, which requires longer processing time on CPU, that new scheduler can theoretically cause more context switches. But it can be tweaked. Future will show if this tweaking of setting will be necessary. But I already heard from clients when they upgraded from Red Hat Linux version 8 or 9 to version 10, which implements this new scheduler, they have seen surprising improvement of Postgres performance exactly in this area, those small bursty workloads. And we quite often get question, okay, this is all nice, so how many connections per CPU are like best option? We must understand that it's not too much about how many connections, because many of them are idle. It's about active connections. So when it comes to that typical transactional workload, modern CPUs usually run very nicely with 4 active connections per one CPU core, but if it is really short, bursty workload, then we can go even higher, up to 6 or 8 really active connections on one CPUs. But on analytical databases, which really process long queries which require hard CPU work, we must understand that one connection per one core, one active connection per one core is our limit. Because otherwise, if there would be many switching, we would see some penalties. And of course, if that workload runs with parallelism, meaning main process starts parallel workers, then we must also add into this calculation that number of parallel workers. So now very quickly, how much memory actually Postgres connection uses. Here is situation when I started Postgres, everything exists mostly as virtual memory, and I started one idle connection on that machine using PSQL, and in top command we can see that resident set size of that process is actually very small. Linux gives us so-called SMAPS kernel interface, which behaves sort of like file, but it's interface into kernel. And reading that interface means short interruption of that running process. So it's not a good idea to scrape it repeatedly very quickly. But that SMAPS output contains memory blocks, how they are allocated and what is the allocation path. And when we use some simple program to summarize it and pivots it, we get something like this. The process was forked from postmaster. This is that first line. Has some anonymous memory and heap memory. Here are some objects on dev.shm memory which are necessary for inter-process communication. And here is line which has very strange name, dev0 deleted, and those are shared buffers. And as you can see, those shared buffers exist in this moment only as a virtual memory, just very small size of those shared objects which are really necessary in this moment. Just this small part exists as physical memory. When I run query and I work hard enough to use the whole shared buffers, then I get this typical situation in top command. And resident set size is immediately very high. But if I look into this SMAPS interface again, I can see that all those huge numbers are actually in this line which indicates shared buffers. If I look at the resident set size of those other allocations, or proportional set size is even better, I can actually see that real memory usage after query ended is quite small, something like 6 megabytes of physical memory being used. But since those shared buffers are being mapped into that process, I see in top command this huge number. And this is typical situation when I run multiple queries in multiple connections. I get huge numbers, which usually exceed physical memory I have available on that machine. If I look into SMAPS and summarize everything, I get exactly these terrible results. But if I remove those shared buffers that dev0 deleted, I see immediately very different numbers. And I can see that real memory usage of those connections is actually quite small, except for some anomalies, which I will explain, because there is a specific issue that heap memory in that connection can actually stay bloated. And of course, where is workmem hidden in all these numbers? To get the answer, I needed to really scrape repeatedly SMAPS output, and then I plotted it, and as you can see, majority of those graphs is absolutely flat. Here we have shared buffers, which just go up and stay there. But here we have two graphs which are interesting for us, anonymous memory and heap memory. And I did many measurements. I have actually already 2 different talks about memory usage in connection when it runs query. Here is some very small example. This is example when data fit into workmem. In this test, I used default workmem 4 megabytes because this is what clients usually use because they don't know better. And if data fit into workmem fully, I see just this very small burst, which takes like dozens of milliseconds or hundreds of milliseconds. But when I plotted those numbers, I could see that even with this very simple query, workmem was used 2 times. So if we see on the internet very comforting calculations like all your max connections times workmem equals you are on the safe side, it is not actually exactly that way. And here is a second example when data do not fit into that work mem. And not that it was used more times, like 2.2 times work mem. What is important on this graph is that the heap memory stayed bloated on level something like 1.5 work mem. And problem here is specific to very small values of work mem, because there are different ways to allocate memory if we have small work mem or big work mem. And if we have small work mem, it is allocated in smaller chunks, and it can happen that at the end of query, process creates something which stays on the top of the heap. And even if Postgres deallocates all that memory below it, from Linux perspective, this process still uses the whole heap. Postgres will say all this memory is empty, and Postgres will reuse it during next query. But Linux says, oh my dear process, I see the whole heap allocated to you. And those are those differences in those connections I showed actually on that previous slide. And there are also some other internal limits of Postgres which we need to be aware of when it comes to too many connections, because Postgres uses this multi-version concurrency control system, and it depends on transaction IDs. And it means if we have many connections, those connections need to check what transaction IDs are still active. And there have been some scaling issues in Postgres 13 and older versions, which actually caused that scaling of that MVCC snapshot degraded quite badly with higher number of connections. It's improved now. There is actually an article from Microsoft blog which explains this stuff. But when I discussed this thing actually with author of this article on another conference, he told me, yeah, it's better, but that scaling is still an issue. So MVCC snapshot is another limit for having too many connections, because simply Postgres must do harder work with more and more connections. So this is another limitation, one internal limitation which we need to be aware of. And another bottleneck in older versions was in number of locked objects in this session, because there was a hard-coded setting in source code which actually limited that number to 16. And problem is that Postgres uses two different locking mechanisms. It uses fast path. This is that locking inside the session, which was unfortunately limited in older version to 16. And everything above it requires lock on shared resources. They fortunately increased it in version 18, and we now have this setting tied to another setting, max locks per transaction, which by default is 64. But if we have too many partitions with many indexes, this number can be also exceeded. And this is another limitation which we must be aware of. It is per session, of course, so we can change it. But it also means that if we change these parameters, first we most likely will need to restart Postgres for having enough capacity in shared objects. But it also means that the whole thing will, of course, consume more memory inside memory context of that connection. So I have just a few seconds to summarize it. We need to be aware that multi-process model degrades with high connection counts and degrades exponentially, not linearly, but exponentially. And those memory allocation tables can be really badly huge if we stick to standard 4 kilobyte pages and have big shared buffers and too many connections. That NUMA architecture actually looked quite nicely when it comes to this issue. We have now new scheduler, which will change behavior of Postgres. We should be aware that having small workvem is not always the win, because there is this problem with bloated heap and those internal bottlenecks with multiverse concurrency system snapshots, and that fast path locking must be also observed. And that's it all. That's all. I thank you very much. I hope it was at least partially interesting for you, and thank you for having me on this amazing conference.